Okay, good afternoon everybody. Thanks for sticking around. And I know the conferences are usually pretty start disappearing. So anyway, I'll try to keep it on schedule so we can wait. So this is what I finished last time. I'll continue on and do this, talk a little bit on seasonal forecasting of stream flows and also extremes, which something that I've been involved with. And then I'll switch over to Bayesian model combination. So in other words, if you have information from multiple sources, how do you combine? And then if there is time, I'll come back to the data. So continuing on with the Bayesian hierarchical modeling, which I sort of introduced yesterday. So yesterday, the Bayesian hierarchical model I introduced and showed an application to stochastic weather generators, so multi-site space-time stochastic weather generation. So today I'm going to use that for seasonal forecasting, so more like a typical regression, and also extreme, so that will be. So here's the application context. So this is the Gorges Dam, and you want to predict the stream flow at this point coming into the Gorges complex. And this approach is sort of typical of what people do in terms of developing statistical models for forecasting flow or other variables. What they do is take the variable of interest and then identify and get predictors from the climate system and then incorporate it into a regression model or modeling framework. So this is simply the data, the box plots of the data from January to December, and this shows that the season of interest is June, July, August in this period. And that's, in fact, it sort of coincides with our monsoon season. Then what they do is they take the time series of the seasonal average, that's the variable of interest that you want to predict for all kinds of management and decision purposes. You take that and then you do a correlation with global climate variables. So you would take the June, July, August stream flow correlated with the sea surface temperatures from the preceding seasons. And one gets maps like this, so you can correlate the flows in June, July, August. You can also correlate the peak flow, correlate the snow in the basin, the snow versus the flows. So basically what you can do is you take the variable of interest, correlate it with all the climate variables globally, and identify areas or regions where you get strong correlation and see if those regions make physical sense. So obviously, you would get some random correlation up here and there, but what you're looking for is much more sort of, there's a coherent correlation here, which from my first lecture I pointed out are these large-scale modes or patterns in climate or climate forcings that we now know as being responsible for driving climate. So you take this, and that's what comes out here in this set of predictors. So these are the regions or areas. So one is 10 degree north, 150 east, 180 east, and so on. So you take these boxes, average these individual variables. So this is sea surface temperature 1 in this region, 2, 3, and then snow from the previous. So June, July, August is summer, so it's snow from the preceding season. So now what you have is you have set of predictors. So in this case it's 4, but then you can imagine to get several of them. So you could get 5, 6, 7. For example, in our applications to the western United States stream flow, so you have about 6 or 7, and then you let the regression model build it out. So you use a stepwise regression or GCD or F-test, or in other cases you can do multi-model. So there's all of those things. So now you have these predictors, and you want to put, so this is the model. So your stream flow, that's the variable of interest. You assume to be normally distributed since it's a total seasonal flow. This is not such a bad assumption, but then again, as I introduced yesterday, the GNM, you can use gamma since it's bounded and positive. So you can use any distribution, but in this case, normal distribution is used. The mean is now related to all these set of predictors. Also notice that here the predictors are quadratic, and that's because a step that I didn't point out is looking at some of these scatter plots of the predictor and the stream flow. There were mild linearities, so we ended up squaring the flows. Again, you can have any form that you can write it out for this. Then you can set up priors, so the betas are normally distributed with some mean and variance, and then the mean is normally distributed with, and so on. And then for the variance, we use half Cauchy distribution was used. Typically people use gamma, but again, for Gelman, this is sort of a mildly informative as opposed to not. And then once you have this, you can construct the posterior and then use MCMC to estimate these coefficients. So this is what you get. So what you end up, and as I pointed out last time, one of the advantages of using the Bayesian hierarchical is that once you have a set of predictors that you are comfortable with, then you don't have to go about choosing. Because the problem with model selection, and this is something we all have run into, is that we use any criteria, be it AIC, BIC, GCV, we run it, and then we pick the model that maximizes or minimizes our criteria. Often, if the data is noisy, if you look at the second best model, third best model, they are not that different in terms of whatever the objective criteria. And then it becomes very tricky to say, why did you choose one? Yeah, just because it happened to be minimum, but then if you dropped a few points or added some noise, yeah, whatever was second could now be the first. And that has always been at least discomfort for me. But here, in the Bayesian hierarchical modeling, or in the Bayesian context, you don't have to choose that. So you look at your posterior and you can right away see that this variable, the variable corresponding to beta phi, is sort of the most in terms of its importance. Next would be beta 4, 2, and then the others sort of come in. They are there, but they come in with large uncertainty. So in other words, you really don't have to choose the variable, rather you let everybody in the model, but each one now comes in with its appropriate importance and its uncertainty. And that I think is sort of the most attractive. So as I said, uncertainty in predictors is modeled and propagated in these forecasts rather. Yeah.
If there are collinearities between the predictors.
Yes, so that's where, so if there is collinearity, what you need to do is do a PCA to sort of read things out. And this is again another technique that is widely employed in climate. So usually you don't have 4, you end up with 10, 15 predictors, and all of them are various manifestations of the large-scale climate. So clearly they all tend to be related to each other, and in which case you have to use, the suggestion is to use a PCA and reduce the dimension, and then do the hierarchical modeling on the PCs rather than on the actual variables. So in this case, since it was just 4 from various parts, so this was justified. But the larger point is that the hierarchical modeling gives you this posterior distribution, and which then tells you how important or how uncertain these predictors are, the coefficients are, and consequently the terms associated with them. So, of course, one of the nice things is you also get the bounds, the uncertainties. So here is the forecast, the observed forecast, and then the uncertainties that go with it. And this is the observed versus predictor scatter plot. So pretty good skill. And the same sort of idea was used in the context of extremes. And so I'm going to give a little background on extreme value theory, and then I'll go to the application. So again, if you recall, recalling our example I showed in my first talk, where you had this reservoir, the American River, which has a Folsom Dam. This is near Sacramento in California, and this was the annual maximum time series. So which is you have all the daily flows and you pick the maximum in a year. And I'll come back to this in a second. And notice that this is when they built the dam, and obviously, as I mentioned before, what was maximum in the pre-dam is now exceeded 6-7 times. And they found that this exceedance is largely due to increase in El Niño activity. So this clearly means you need to have some way of being able to model non-stationary extreme. So typically what is done in practice in engineering, when you want to build a dam, you go and compute the 100-year flood. And the 100-year flood is essentially computed based on the observations that you have until that point. So for example, if you want to build a dam at some point, build a dam in one of the places here, you would collect annual maximum flow data, and then fit an extreme value model and estimate the quantile corresponding to the 100-year return period. And then you would say, this is the 100-year flood, and I'll go build for that. Clearly, the 100-year flood in this case has changed, as you can see from just looking at this. So how do you quantify this? And the 100-year flood or any other return period flood is also used for management. So every year, if you want to manage your floodplain, if you want to manage your reservoirs, you need to make a prediction of 50-year return period, 100-year return period. If you have a single extreme value model fitted to your data, then you have a single 100-year flood. That is what is used no matter what the year is. We'll get to that in a second. Okay. So this area of non-stationary extremes, and consequently the non-stationary or adaptive flood risk estimation is very, very important. So you just can't have single 100-year flood and then say that is what you need to plan year after year, when it might be that in a certain year the conditions just don't conspire to produce a flood, but you are now preparing for a 100-year flood that is way more than what is warranted in that year. Again, this is to show that there's non-linearities between floods and all these climate variables. So clearly something has to be done. The stationary flood model, where you just take the data, fit an extreme value, is not going to work. And this is another example to show that, for instance, floods over California are largely determined by what are known as atmospheric rivers. So this is typically moisture that starts out in the Western Pacific and then sort of transports itself through these very coherent, what are known as atmospheric rivers. And in fact, when one of these forms in the satellite, you can predict them almost 10, 15 days ahead of time. And the magnitude, the strength of these rivers, they are linked with large-scale features throughout the ocean. The point being that when you see a flood on land, it has origins coming from way back. And once you know these pressure points and what they trigger, then you have excellent predictability. So simply using a stationary model is not going to be helpful in situations like this, where there's increasing understanding that large-scale climate plays a significant role in what happens from year to year. Okay, so a quick tutorial on extreme value analysis. So again, we're all familiar with the sum stability theorem, which is if you have identical IID, random variables, then the sum, then T being large, tends to normally distribute. So that's that. So the extreme value theory comes from what is known as max stability. So rather than summing up numbers, bunch of numbers, and then looking at their distribution, which as numbers get large tend to normality, you are now taking maximum or minimum of a bunch of numbers. So you have IID, and then you pick the maximum. And now you have M sub T, so it could also be minimum, so it doesn't matter. So in other words, you pick a block of numbers, and you generate a block of random variables, and then you pick the maximum, which is also a random variable in itself. And this turns out to be distributed as this GEV, or generalized extreme value distribution. And this is what is known as the max stable or max stable theorem, which is to find distributions for which maximum has some form as the original sample. And why is this important? Typically, when you're dealing with floods, the variable that you're interested in is maximum of bunch of daily flows, or maximum of bunch of daily precipitation, daily temperature, if you want to model heat waves and so forth. So there's lots of applications, not only in meteorology, but also lots in financial sector, where you're looking at maximum of a stock price over a certain time period. So you have daily information or whatever time. So this GEV has three parameters, eta, mu, and x, of course, shape, location, and scale, just like any other. And the shape parameter is the one that tells you whether you have a long tail, whether you have a thin tail. So if your shape parameter is 0, then it's a light tail, also known as a Gumbel type distribution, widely used by hydrologists for modeling floods. And so in other words, the domain of attraction for this type is more common distributions like normal, log normal. So in other words, if your data x1, x2, x3 came from one of these distributions, then typically your maximum tends to go to gum belt. And that's why hydrologists use this, because stream flow is assumed to be one of these. And if it is greater than 0, then it's the Fréchet type distribution, which has a heavy tail. And I'll point out in a second, it is these, in samples, finite samples, you can get mostly Fréchet type distributions, which means you need to consider fat tails. And that right away means that if you're looking at a 100-year event, so which is a quantile, let's say the area about that is 0.01, then clearly getting that quantile from a fat tail distribution versus a thin tail makes a huge difference in terms of how you manage risk. And that is sort of the key. And then lastly, if it is less than 0, then it's bounded, it's the typical vapor. So one might ask, why not simply use one of these distributions? So after all, if this is the data that you have, and if these distributions fit those, why do you need to know the maximum of that? And the answer is very simple, which is all of these have very thin tail, and if you're interested in maximum value, then theory tells us that you can get this GeV, which has the ability to capture fat tails, and that's the key advantage of that. There's another companion modeling distribution for extremes that is known as peaks over threshold, or POT, and that turns out it is distributed as this GPD. So here what you do is that, and this happens in many situations in hydrology, in environmental engineering, in finance. So for example, in environmental engineering, if you have a pollution problem, you are only interested in what is the probability that some variable exceeds the threshold. You don't really care about what happens if it's below, because there's no action taken. But when it hits a certain limit, exceeding that is more important. And modeling excesses or exceedances above a threshold, again, is fat tail coming from theory here, gives you what is known as GPD, or generalized Pareto distribution. So these two together enables you to model sort of a wide range of extreme events. Yes?
Sorry,
yeah.
Why do you need the conditionalization on X-ray? Isn't that included in the definition itself?
So in other words, yes, here it is. Yeah, it's written. So basically, when you choose a threshold, all your modeling is all x that is exceeding that threshold, and this gives you substantially fatter tail or heavy tail in that really extreme range, which none of the. So in other words, you could have situations where where your data might be conforming to one of these distributions. You can do your KS test or QQ plots, everything looks fine. But then when you start using it to infer extremes, given that you have heavy tails, then you tend to be poor in your estimates and predictions. So that's sort of what motivated us. Okay. So what we then did, or what was done by one of our co-authors, Rick Katz, sort of put all these things together, is that you could take these coefficients, mu, sigma, eta, and then write them as a function of covariance. Okay, so in other words, so you take the generalized GeV model, and then look at these parameters, and then you can say, well, have a hierarchical model where your y is GeV distributed, and then these parameters mu, sigma, and eta a la GLM is now a function of covariance. Okay, so that way what you can do is you can let this GeV vary from one covariate situation to another, rather than having a single fixed GeV model whereby you're stuck with a stationary. And again, since you are prescribing this, it sort of nicely falls into the hierarchical framework. So a couple of years ago, we organized a summer school. This was in Boulder, and it was about 2-3 weeks with graduate students and researchers. And Gilliland and Katz, they put together this beautiful extremes toolkit. It is there in R. And as part of that workshop, we also had hands-on training. Students had to do projects. And in fact, a couple of those projects actually are coming out as papers. So you can go to this webpage, and there's a link to that, the workshop, the extremes workshop, and you can see all the speakers, and in fact all the talks are online and everything. So this is something that I would consider or think of maybe organizing as a follow-up to this, because there is a lot of interest in this extreme value in terms of its applications. to variety of fields, and it sort of blends nicely with traditional approach, Bayesian approaches, and so forth. So anyway, that's my pitch. Okay, so back to the Three Gorges Dam, where, yes?
Sorry, can I just get the URL?
Oh, yes.
Thanks. Sorry.
No, no problem. CAD's extremes that I get to Rick's good, nicely organized web page. So yeah, so it's very easy to use, and in R, it's you can do both POT analysis, you can do GPD, and you can also do with covariates, without covariates, and it's very user friendly. So again, now you can take the peak stream flows and do the same analysis and identify those predictors. And now what you have is your Y is Gumbel distributed. And then the parameters of the Gumbel are functions of your covariates. And then you have the same sort of framework. And now when you do the Bayesian hierarchical modeling on this, you are now modeling the peak flow for every year. And what you then end up getting is, again, like as before, the covariates, the posterior distributions on the beta stereo, how these different variables are in terms of their importance. And then you get the uncertainty, the predicted value for the peak. And the other thing, next slide. Yes. So this is what I wanted to sort of come back and circle, which is if you simply use a single GeV on the annual maximum flow at the Three Gorges, this is what you would get, those horizontal lines. So the horizontal lines are your stationary 50-year flood, whereas the blue is the non-stationary 50-year flood coming from the Bayesian hierarchical model. So remember that for each year, what you get from the Bayesian model is the parameters of the Gumbel, which means the entire Gumbel distribution that is appropriate for that year. And from that you can read off the 50-year return rate flood, and this is what you have. And the red is the actual observed annual maximum. The point I want to draw here is, let's take this year. So this year, the observed was much lower. And if you were sort of planning your decisions in terms of staging resources or what have you, reservoir, you would be planning in terms of this value, because that is the stationary flood. Whereas this year turns out, based on the covariates, based on the climate conditions, that you have a much lower chance of getting high flow. But then if you were simply going by this year after year, which has been sort of the typical way people do, use a stationary approach, now you would be wasting resources, or your decisions wouldn't be very efficient, and that's sort of the idea. And then also, this thing explains features like this, where after 1940 you have a lot more. So if in your predictors, if you have those covariates, the ENSO and other things that impact occurrence of extremes, you will have a better shot in terms of being able to simulate these situations much ahead of time. So thereby, if you are trying to build a reservoir here, then you can say, well, based on the non-stationary model, there is a potential for increase in risk, so which means you would want to appropriately modify the reservoir size or whatever the capacity.
So have you hypothetically, retrospectively used extreme value analysis on the American River, and if so, what height dam would you have built?
I haven't used on this one, and I should. I've been giving this example a lot, but I've used it on a couple of other situations. One is in Montana, and yes, so you do get a good modeling of. So clearly, I think in this case,
you would get a taller dam.
Exactly.
And
now there will be other issues. For example, people would say, why do we need to go that high? And so because remember, each time
politics.
That's politics. Yeah, exactly.
Engineering and politics.
But each time, yeah. So I think certainly you can do a much better job of being able to tell that your 100-year flood based on the stationary extreme value model is going to vastly underrepresent.
Well, probably helps your story if that dam turns out to be taller than what shows up in.
Oh, definitely it will be. Yeah. So then there are other points. Is it is it better to do a extreme value on the entire distribution or just on part of this? Because depending on which part or which segment, your 100-year flood estimate will change.
Definitely whatever you come up with 1940
Oh, yeah.
will be different from 2000.
Absolutely, no questions. In fact, there is here. So what happened here? So here is the answer. So we did a 21-year moving window, 100-year flood estimated from the dumbbell on this, and then the 50 years. So notice that. So if you were in 1940, this is sort of what you were looking at versus.
Sorry, what's the dotted and what's the solid?
So one is a 50-year moving window, another one is a 21-year moving window. Okay, and what we also did, we applied this we applied a non-Bayesian version. So in other words, we had all the hierarchy minus the priors and such, but otherwise everything else was. So that we applied for water quality, and this is a very, very nice example that I like. So this is a situation in Portland, Oregon, and what you have is this river here. So Portland is served by this river, and they do no treatment. So water comes out of the watershed, they add chlorine and just distribute it. So the problem is, whenever you get a heavy rainfall, you get a lot of sediment getting into the treatment plant because sediment gets washed away from the watershed, and once it gets into the treatment plant, your turbidity goes up, and if it is high enough, they have to shut it off and resort to groundwater, which means pumping cost and so forth. Because they don't have any backup, unlike typical other water treatment plants where you have elaborate treatments. Here, the treatment is simply just whatever comes. It's called forest to faucet program. So the flow is sort of a determinant. So the maximum flow coming into the river is a determinant of how high your turbidity is going to be. And so that's what it is. So no physical filtration, simply chlorine is added and set out. So you have precipitants leading to high flows, which then leads to turbidity exceeding 5 units. Actually, that's greater than 5. And if it exceeds, then you are looking at increased pumping cost. So this is the high flow that we wanted to model using extreme value distribution. So here is what we came up with. So our model for the GEV was one where the rain and the temperature was cross product, so which means this is a nonlinear model. So again, writing it as a hierarchical enables you to bring in predictors that are, you can have product terms and interaction terms and so forth. So in this case, the best model turned out to be for the location parameter beta naught plus beta 1 times R times T, it's the rain times temperature. And again here too, so here you can see the observed is the dots. The horizontal lines are the 10th and 99th quantile, and then the blue is the conditional, and then this is the observed. So these are the observed. So this is the model for 10, model for 99. So notice that if you're planning for a 100-year event, this is the value that you would be planning, whereas in many years you have much lower values, so which means you could free up resources, or in years such as here, where the 100-year flood is more than the stationary 100-year flood, that means you would have to, bring in more resources. And then you can also look at individual years and see how the GEV varies. So this is for 2005, 2006. This is the observed flow, and this was the distribution for 2005. So notice that, and this is your stationary GEV, the black PDF. So which means that if you have if you are using the stationary, you will be predicting the 100-year all the time here, whereas depending on the climate, the PDFs shift. Lastly, one could also use the climate projections coming from IPCC to get your precip temperature and propagate it through your model, and you get projections of maximum flow for these different epochs from the GEVs. And then you can run it through to get your cognitive exceedance of turbidity. So I'll skip that. Okay, so I'll move to Bayesian model combination, and then if I have time, I'll come back to Bayesian. Okay, so here, this is work that I did around 2001, and it's still being used, slightly modified and improved. But as I pointed out in my lecture 1, the climate system, when they make climate forecasts, you have to contend with a lot of uncertainties, initial condition uncertainties, boundary condition uncertainties. So the way forecasters get around is by running ensembles. So they take a model and they know that you cannot have a deterministic one run based on with the starting initial condition. So they make several runs and then they give you an ensemble. Once they give you an ensemble, then you can look at the PDF. And then using that PDF, various things are done. So you need to combine information in a more coherent, optimal manner. And what is also done is you get ensembles from several modeling outfits. So the NOAA model produces a bunch of ensembles, the European model produces a bunch of ensembles. And now you want to combine all of them in a coherent manner that comes up with a sort of a coherent, optimal combination, so to speak. And that's where that's what motivated this. Again, this is a picture of the Earth with the model blanket thrown on top of it. And as you can see, there's several layers on top. So you are basically solving Navier-Stokes equation every time steps, crudely speaking, forward in time based on the initial and boundary conditions. So the point I want to emphasize is that even though ensembles produce PDF, these ensembles are not large enough. So they are often 10, 6, 7. So it's hard to give a PDF. So unless you have 20, 50 ensembles, and that's not going to happen given the computational cost. So what is typically done is they take these ensembles and convert them into categorical probability. So they say, okay, what is the probability, or how many ensembles fell in category 1, 2, 3? And these categories, again, obviously, of course, you can have 10 categories or 15, but typically it is 3 because that's the most skill these models have currently. And these are typically done at tercile, so which means it is what is the number of ensembles falling in the first tercile, second tercile, third tercile. So because you are looking at ensembles and categories, right away that puts you into multinomial. So which means, as was talked before, earlier, the Dirichlet prior or Dirichlet distribution is sort of the more appropriate that comes out here. This is just simple just notation. You have X, T is number of years for which you are issuing a forecast. These are seasonal, so it could be DJF, March, April, May, and so forth. And then you get ensembles from general circulation models or climate models. YJT, M being the ensemble member, time again, and then we classify into K categories, and this is the situation. So for climatology, since you're classifying into 3 equal categories, the probability of being in each one of them is 1/3, 1/3, 1/3. And then you run the model and get the ensembles, then you get a probability P1 in category 1, P2 in 2, and 3. And now the question is, how do you combine the two together? And that was the problem that we worked on. So again, the Bayesian modeling sort of tends to be appropriate. You start with the Dirichlet prior because you have 3 categories, so this gives you the categorical probability. So this is the Dirichlet distribution, and this is the mean variance and so forth of that. So what you're interested in is what is the posterior probability given the model, right? So that's what you're interested in, and because you have 2 models here, so one is this equal probability model, and we call that in the field it's known as climatology, which means that that's what you would get without running any model. That's the null model that you have, right? So if you have 3 categories, it's 1/3, 1/3, 1/3. And then you have the other model, which is the climate model that you run. So basically what you have is this term W, or the weight. So you're weighting one of the model W, which means the other model has got weight 1 minus W. So all we have done is taken the Dirichlet distribution and then regularized it with the weights. And how do you get the weights? You compute the likelihood function and then you maximize that. So that's sort of very simple.
So
Yeah.
you have two Dirichlet prior distributions, one with a 1/3, 1/3, 1/3, and then you have some other informed
Yes.
Dirichlet.
That is from the model.
Oh, so there's only one.
Yes.
So it's an uninformed.
It's uninformed. Exactly.
And then the likelihood is your multinomial likelihood.
Exactly. Absolutely.
So if you had some information to suggest otherwise from the equal proportion with 3 categories, we could have
Yes.
different Dirichlet.
Yes, you can have a different district, exactly. But as I said, it is customary to issue all these, the forecasts that you get online. If you just go, for example, NOAA and other places, they'll give you 3 category probability, equal category. So this is just a simple sort of math that gets you to the posterior and you can look it up in the paper. I won't go into the details. The way you end up modeling is, so this is the extension to any general. So in other words, if you have more than one model, so that's why the J go from 1 through J, which is J models. Okay, so in this case example I'm going to show you, we have 3 models and then climatology, so totally 4. So how do you evaluate skill? So when you are predicting or modeling in a regression sense, then you have RMSE, you have correlation coefficient between observed and predicted. You can do all kinds of things. But when you have 3 probability numbers, how do you go about evaluating how good your skill is? And Kevin pointed out in his previous talk, so it was a nice setup. So these are some of the things that sort of widely used in climate and weather forecast. So this is something we proposed, which is known as the likelihood ratio. It's nothing but the likelihood from your forecast relative to likelihood from a null model. And in this case, it's climatology. Okay. So let's say if you have 3 equal categories, then you're issuing this forecast year after year. So the likelihood is basically 1/3 to the power n for climatology. And assuming your forecast is perfect year after year, then your likelihood from the forecast is 1 to the power n, and so your likelihood ratio is 3. And likewise, if your forecast is poor, then you end up with, or if your forecast is no different from climatology, if it is exactly the same as during a coin, then your likelihood ratio is 1. So essentially what you have is these bounds, 1 and 3, less than 1, you're worse than, worse than throwing the, so you're worse than, worse than climatology. Anything greater than 1, you're better and better relative to climatology.
Yes, if you take this uninformed one, 1/3, it's like a straw man.
Yes.
So if you use a more informed so-called null model.
No, the problem is these models are there is very little skill in most of the time that it is so hard to beat 1/3, 1/3, 1/3. And that's why that's why they even go to 3 categories. So you could ask, when you have 10 ensemble, why not give 5 categories? The thing is, 3 is sort of the most they can get some skill. Anything more than that, it's terrible. So 1/3, 1/3, while seeing crude, beating that in many cases, and you'll see in a second in my results, is not that trivial. So because when you don't have a signal, in many times the seasonal predictability comes from when there is an El Nino going, or the normal years are difficult to predict. That's why when there is normal, these climate models have difficulty predicting. And now you compute the skill over, say, 50 years of forecast, where 30% of the time it's normal and the skill is just terrible. Your overall skill is much lower, so your 1/3, 1/3, 1/3 wins out most of the time. Same thing with the Indian monsoon forecast. The IMD issues forecast normal, 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 and if you look at the skill overall, very good. But then the times when you really need it, they do horrible job, like last year and 2002, 2004, when you had the severe drought, they just keep on issuing normal. So from their point of view, that's the good strategy, right? So most of the time, and they will tell you, if you talk to IMD people, that's what they'll tell you. We have been very good in most of the years. Yes, the ones you were terrible are the ones that is of importance. Other years nobody cares. The other one that is used widely is this RPSS, or Rank Probability Skill Score. So this is simply taking the difference between the CDFs, between the 1/3, 1/3, 1/3 probability, that's this, and then the categorical forecast coming out of it. And then the difference, there should be a square here, and that gives you the RPS for the forecast, and then you have the same thing for climatology. And again, 0 means 1 is a perfect forecast. Okay, so now to some results. So this is the forecast for January, February, March precipitation, likelihood ratio. The 3 models that were used. Notice that there is hardly any skill in most of the planet. So this is winter time, so you get some skill here, as you would expect. In one model, not anything here. Of course, over India, there's nothing going on during that time zone. But otherwise, you can see there's coherent skill in Northeast Brazil, that's ENSO signal, and then West Pacific ENSO again. So you have some places where the models have some skill, but otherwise, most of the time, there's nothing. And by the way, precip is very difficult to get, as you all know. So then, this is the weights. So now we combine. So if you combine, this is the skill. So notice that when you combine, when you take all these patchy stuff and combine it, you get, you get a much coherent signal here, and then you get into values that are higher than 1. And these are the weights for these different models. So this is the weight at each grid point. By the way, I forgot to mention the Bayesian approach is applied to every single grid point forecast. And this is the weights on climatology. Notice that climatology gets a lot of weights.
Are they treated independently?
Yes, right now this is treated independently, but otherwise one could think of, we didn't know how to do it any other way because the models are spatial bias as well. And so for example, for India, they put a lot of rain in this region, but then a lot of it is on the oceans. But people assume, yeah, it is on the oceans, but it's actually on the land. And so there are things like that which are difficult to correct for, maybe some stretching algorithms to pull things out. But for this, yes, it's assumed independently. Likelihood ratio, this is for equal weights. In other words, why go about optimizing? Why not just throw all the 3 models and do an equal weighting? And that's what this is. So if you do equal weighting, it's pretty poor because there is information in these models at different levels. So you want to combine them based on their past performance and past skill. And when you do that cleverly, yeah, you improve quite a bit. And this is for Africa, and this is to show for 2000, these were the categorical forecasts for the 3 categories after the combination. This is what was observed, was predicted in 2000, and this is what happened actually. And just to give you a point, up until 2000, until I put together this algorithm before I left Columbia, this is what they used to do. And what they used to do is take the forecast coming out of these models, and then 4 people would sit with all the maps put together on a huge table, and they would pour over it for days, and then they'll say, we think you should put a line here. So that's why these lines are all these, wiggly as if somebody drew with crayons. It's just because we think the model doesn't have skill here. I'm going to trust this model more. So it was just awful. I mean, there's a lot of subjectivity that would go in. Some people, when they had some axe to grind in terms of forecast, would nudge things one way or the other. So this at least got rid of all of that and made it much more, at least a starting objective point. So,
this kind of seat of the pants forecasting is still going on in a lot of places.
yes, and I wouldn't say fully seat of the pants because there is a model output that comes up, and then they have some prior knowledge of, if there is an El Nino, then they know, yes, these places should be dry. And then they say, well, the models don't do a good job. And they also can look at what's happening right now because these are April, May, June forecast. Yeah, so
well, it's informed, yes.
It is informed.
This sounds an awful lot like what the Bureau of Meteorology in Australia tells me.
And I think, to be fair, not to beat up on this, it is difficult. Whether, as I mentioned in my first talk, it's not easy, but it's fun, and the nice thing with prediction is, again, the good and bad things. The bad thing is you stick your neck out, and then you become infamous very quickly. And the good thing is, if you improve and if you do a good job, and people use these forecasts. In fact, it's amazing how this is 2000, but now these have gotten better and better. And after I left, they took this algorithm and improved on it further. But the point is, lots of people now use this: commodity traders, insurance, risk managers. So there is just simply, even with modest skill, when you're dealing with billions of dollars, just a few percentage change in your skill, it means you're talking hundreds of thousands of dollars. So this is how it comes out right now. So notice that all those crayons are gone. That's because the Bayesian objective. So all they do is, once they get the combined forecast, then they sort of combine the regions that are coherent, and you see that it is a lot more intuitive rather than this weird. So for example, what is the reason to simply just arbitrarily draw something? So anyway, so this is the latest forecast for North America, January, February, March 2013, and it calls for a drier southwest US. So this means 45% chance of below normal rainfall, or rainfall being in the below category, 35% chance being in the middle, and then 20% chance being in the above category. So you have these 3 categorical numbers that come out, and this is now put out every month. And if you can go to the IRI website, it's beautiful. There's lots of information, and then you can pull whatever region you want. They have forecasts archived up to 2000, and this is issued every month for 2-month period, 3-month period for all parts of the globe. And you can take these categorical forecasts and then you can do downscaling. So in other words, if you're a water manager inside one of this, and this is your categorical forecast, you can then take that and resample your historical data to reflect that probability and then tell your forecast margins. Okay, so I'll stop there. So there are a couple of other examples, and I can put it up online in my talk. PPT file. Thank you.
Thank you.